Today, we want to talk about the divergence of a vector field. Let's think about the idea of the divergence. Let's think about how we can define the divergence, and let's see where the divergence fits in the greater scheme of calculus thinking. Let's make a note of the things that we want to do. What's divergence? How do we calculate? And then how does it fit in the calculus lore? In case you look up something like the lore of calculus and you don't find anything, that's because I just made that up. Made up this kind of lore of calculus. Where does it fit? The story of calculus. Oh, that's even better. All right. So the first thing we want to think about is, what is divergence about? Sorry, it just occurred to me, do I want to do these in some kind of other order? No, let's talk about what's divergence. What's divergence? So the other term that we have for divergence is flux density. Flux density. Flux density. The big clue as to where this sits in the lore of calculus is that this is the we're going to be calculating the flux density, and this is specifically at a point. Divergence is flux density. Specifically, we're thinking of flux density at a point. How much flux is happening at this point? That part right there where I said the flux density and in parentheses at a point really tells you where this sits in the lore of calculus, where this sits in the story of calculus. Divergence is a local thing. It happens at a point. It's a way, something that we're thinking about happening at a point. So in that regard, it sits in the derivative category. So at a point is strong evidence. That's pretty strong evidence that we're thinking of divergence as some kind of derivative. It sits in the derivative category. Remember, when we first calculated the derivative, our goal was to find the slope of the line tangent to a curve at a point, a local thing. Since this divergence is a local thing, derivative is a local thing. We're looking at how much something is changing at a point. That's a local thing. That's a derivative. That's our derivative thinking. So what we want to think about is, if we have the divergence of a vector field, we want to imagine a sphere around a point, and we want to imagine the flux through that point. So it's going to be calculated using a flux integral. So let's think about flux density. Since we're calling this a density, it's how much of something is divided by how much space it takes up. How much of something there is divided by how much space it takes up. That's what density is about. In this case, how much flux divided by how much volume. Thinking in terms of math, density just says how much stuff is there divided by how much space it takes up. So this is going to be flux divided by volume. Because we're in R3. So the divergence of a smooth vector field F, what we're going to do is we're going to take the flux flowing out of a sphere. That sphere is eventually going to shrink down to a point. This is like the slope calculation. We're going to take the flux out of a sphere So S is going to be a sphere centered at the point X, Y, Z. And the flux, we're just going to calculate the flux of the vector field out of that sphere and divide that by the volume of the sphere. How much flux divided by how much volume? The amount of flux divided by the amount of volume. So our numerator here is the amount of flux that we calculate with a flux integral like we were talking about last week. How much of the vector field is flowing out through the surface? But this is flux density at a point. We want to know what's going on at a point. So we're going to take this sphere, and the sphere is going to shrink down to a point. Now, that would cause us to divide by 0 because the volume of a point is just 0. And we can't divide by 0, so we have to play the calculus game. Since we want to know what's going on at this point, we'll take the limit as the volume of S goes to 0. Because we want this at a point, we'll take the limit as the volume of this sphere goes down to 0. Now, for this, we're using a sphere in this case because it's easiest to see. Imagine a sphere shrinking down to a point. But we can use any kind of shape that we want. Almost any kind of shape we want. We have some kind of volume that's shrinking down to 0. It doesn't have to be a sphere. Could be some other type of volume. It's just easier to picture a sphere shrinking down to a point. What we want to think about, what we want to see in kind of the lore of the calculus, in the story of calculus, what we want to see is us, this wants to trigger a memory back down to where we were thinking about calculating the slope. This at a point part is the part that is the part where we divide by 0. We want to find the slope of the line tangent to a curve at a point. So we know that this is the derivative. And it's the change in y divided by the change in x. And because we want this to happen at a point, we take the limit as the change in x goes to 0. We're looking at how much change in y divided by how much space that takes up. And in the case of the slope, we're dividing delta y divided by delta x. The space it takes up is just some interval. What happens when that interval drops down to 0? That's what we're thinking of for this at a point business. That is the calculus thing. So this derivative business has always been about some kind of density, where the space that the change takes up is dropping to 0. We have to use this flux integral for the numerator because that's how we calculate how much flux we get through a surface. So this numerator is the flux of the vector field through the surface S. When that surface S drops down to a point, we get 0. When that surface S for the flux, and when that surface S drops down to 0, we get a volume of 0. We have 0 divided by 0, the indeterminate 0 divided by 0, which is the same thing that happened when we found the slope of the line tangent to a curve at a point, f prime. The change in y, when the points got closer together, the change in y got smaller, but the change in x got smaller as well. We were looking at, once again, a 0 over 0. So that's what divergence is. Divergence is flux density. We want to imagine how much of at a point, how much of vector field is flowing out through the point. We can think about how to calculate. We need to think about how to calculate divergence. I spelled K wrong. So notice that this del operator is a vector. It's got an I, J, and a K. It's a vector. Notice that it's not a function on X, Y, and Z. It's an operator that we're going to apply to functions. So it's not a function of X, Y, and Z. It's not a function of points. It's a function of functions. So this is the thing that operates on points rather than on the variables. I think I said points. It operates on functions. See, the problem with long weekends is that they are rare, and so we don't get a lot of practicing coming out of long weekends. If every weekend was just a 3-day weekend, then 4-day weekends wouldn't seem like such a big thing. It wouldn't be so hard to pull out of. But since we've decided that we can only have 2-day weekends, we can think of our functions as being operators on the variables, the points themselves, operating on X, Y, and Z. But the del operator is operating on functions. The places that we've seen the del operator are the gradient. So the gradient of a function is just del of that scalar function. This applies to us when we apply the del operator to a scalar function, we end up with a vector field. The del operator and so the gradient will give us a vector field. So it's a gradient when we apply it to a scalar function. This is very similar to what we saw when we had functions of one variable, but with functions of one variable, we don't have partial derivatives. And if our vectors are only one-dimensional, they're just scalars. So in this category, we could like C also. We don't have partial derivatives if there's only one variable. So instead of the partial with respect to xi, we just say the derivative with respect to x. And we don't need to say I because it's a scalar. So we've been dealing with this gradient business all along. We also, back in the day when we had single variable calculus, we didn't say the direction of maximum increase because there's only one direction. We only had the x direction. So life was super boring back then. That's why Calc 1 was so simple. So the del operator is a vector. And so we can apply the del operator. This is applied to, oops. Here's the del operator applied to a scalar function, but we can also apply the del operator to vector fields, vector functions. The divergence is the dot product of the del operator and the vector field. So if I hand you a vector field and ask you for the divergence, this is how we will do it. So if f is, so the del operator is partial with respect to xi plus partial with respect to yj plus partial with respect to zk. Dots are vector field. I didn't specifically state that the vector field had the three scalar components f1, f2, and f3, but f1, f2, and f3 are the scalar components, scalar functions that are components of the vector field f. And we should note that f1, f2, and f3 are all functions of x, y, and z. I just didn't want to write of x, y, and z so many times. But we can see how it works out. We have the partial of f1 with respect to x plus the partial of f2 with respect to y plus the partial of f3 with respect to k. We're getting a scalar function. Of course we are. We're calculating a dot product. A dot product will always produce a scalar. So we have the del operator applied to a vector function or a vector field. Note that this is a dot product, so we're getting a scalar function. The result of a dot product is a scalar. In this case, it's a scalar function. Just like in a single variable calculus, we looked at df, dx, and we said that this is a function that told us the slope of the line tangent to the curve at a given point, delta y over delta x. What the divergence is telling us is how much flux we are getting through a sphere at a given point. But we're looking at that sphere the volume of that sphere dropping down to 0. How much flux at a point, flux density. Last partial should be with respect to z, not k. Thank you. Well done. You found my carefully planned mistake to make sure people were paying attention. 0 points for you, minus 1,000 points for everybody else. I'm just kidding. It's minus 10,000 points for everybody else. I'm just kidding. I remember what I was watching, but they were referring to something going on. It was kind of recent, but they were referring to something going on in a video game. And I could tell how old the writers were because they referred to how many points a person was scoring in a video game. And all I could think is like, oh, you don't score points in video games anymore. I mean, like the most common video games. Like how many points do you have in Skyrim? I mean, that's just not a thing. Anyway. Partially because there's like this gigantic inflation in points. Like if you find an actual old pinball machine, you get a replay if you score like 100,000 points. And then there was a Terminator pinball machine when I first went to school. And to get a replay, you had to have 32 million points. And I thought, that's ridiculous, 32 million points. And I played for like 30 seconds and I had like 10 million points. And I go, all right. It's just inflation. It's just inflation. The numbers are just bigger. You know what I mean? Y'all know how inflation works? Measuring things like how much things cost in dollars, that's a local thing. That's like a derivative. Like how much something costs in dollars is kind of a stupid calculation, especially if you're going to try to measure things throughout time. And then using those ancient calculations and then trying to apply math to them is really dumb. When my grandparents bought my mom's house, they paid $30,000 for it. That doesn't really mean anything. I mean, it's fun to shock young people, say, hey, I see you just bought a Civic. My grandparents bought their house for that. Like a new Civic. Maybe a loaded Civic, but not like a Type R. Aren't Type R's like $50,000? Anyway. What are we talking about? Oh, yes. So we want to think of divergence as flux density. It's tied to our new vector calculus thing of a vector field flowing through a surface. The surface happens to be a closed surface, so we can think of the vector field flowing out through the surface. But we're calculating a density, so we want to know what's going on at a point. Or sorry, we're calculating a derivative, so we want to know what's going on at a point. So we're taking this volume and dropping it down to 0. This is the same kind of thinking that as when we found the slope of the line tangent to a curve at a point. We took the change in y divided by change in x. And then we looked at what happened when the change in x dropped down to 0. We were looking at 0 over 0. And the question was, what 0 divided by 0 are we looking at? What is the value of 0 divided by 0 in this case? So that's what that's the indeterminate form we're working with. Your derivative indeterminate form is 0 divided by 0. L'Hopital is more of a how to calculate something. rather than how we think about something. There's a lot of times, sometimes we use L'Hopital's rule and it works out, but we end up in kind of a loop, not to a point where it really matters, but we don't want to think of L'Hopital's rule as being, we want to think of L'Hopital's rule as thinking of a way to calculate some limits for indeterminate forms rather than what we're calculating when we calculate these limits. Yeah, it's more of a this is what we do rather than this is how it works. L'Hopital is more following a recipe than understanding why you do the things in a particular order in a recipe. There's a reason that you put your aromatics in first. I don't know what that is. I just do that all the time. There's always just onion first. If you want to be a better cook, get yourself a cast iron skillet, and before anything that you plan on cooking, cut up an onion, put it in some oil, and let it cook for kind of a long time until, and keep stirring it so that the onions don't stick. If you want to be fancy, use shallots instead of onions. And then after that's been going for a while, then you put your garlic in. Any questions? Not about cooking, because I can't answer questions on cooking. I know how to cook certain things, but that's like knowing how to find some derivatives. That's not really knowing calculus. That just means you can find some derivatives. So here's how I want you to think about divergence. I want you to see divergence as a derivative, and it's the flux at a point. The flux density at a point. Flux density at a point. This modifies our view of slope. Think of slope as a change in the function density at a point. All right, that's it for today. I will see you all on tomorrow. Hey, everybody have a good day, and thanks for playing. I posted some problems for you to look at. They're not necessarily the problems that I'm going to use on the final, but they are sources of inspiration. So check those out, and I'll see you on tomorrow.